Hello, everyone. We are the capacitive tab water team. Our team is composed of Juan Rosas, Telman Aziz, Giovanni Arceniga, and myself, Michael Guido. Welding is a common practice when it comes to joining two pieces of metal. It is a more advantageous process than soldering when it comes to making battery packs and thermocouples. A little bit about the background. Capacitors are energy storage devices that, unlike batteries, can quickly store and release energy without being damaged in the process. Capacitive discharge welding is a type of resistance welding that involves heating up a resistant load near the material's melting point using a short pulse of current obtained by shorting a capacitor. I will now pass it on to Sal.
Hey guys, I'm Sal. I'll be talking about the experimental setup and a little bit about the test plan. Starting off in figure 1, you can see our project schematic. The welder uses a 3.5 farad capacitor that can be charged up to 17 volts for an energy storage of 500 joules. To perform the weld, we have an Arduino send a 5-volt signal, generally a pulse that lasts a few milliseconds to the gate driver, which then amplifies the signal to 12 volts. Before reaching the MOSFETs, and the MOSFETs act as a switch allowing around 3 kiloamps of current to pass through from drain to source, this shorting the capacitor to do the weld. Going on to the experimental test plan, our team was tasked to complete the tab welder left behind by the previous team. We share a lot of similar things with their tab welder, and the only things we really have to fix were the MOSFET and creating new PCB designs and just implementing our thoughts. For the MOSFET PCB, we had to ensure traces could handle over 3.6 kiloamps using 20 MOSFETs, divides the current between them, and this reduced the thermal energy lost, which Gio will talk about. So I'll just pass it on to Gio so he can talk about it.
All right, so for the further testing of the heat sinks for the MOSFETs, we used ANSYS Workbench to create these simulations. We used a transient thermal analysis to represent the pulses that the MOSFETs would be subjected to, and we found that the over a 2-minute time period with 5 pulses over about 30 seconds, we found that the temperature of the MOSFETs would not exceed a 2-degree temperature change from its ambient temperature of 28 degrees Celsius. As for the microcontroller PCB, we left it mostly unchanged. We kept most of the same connections. The only change was the gate driver and spacing for more secure connections. On experimental results, we did test the circuit resistance, which included the MOSFET board and electrodes, and we found this to be 4.7 milliohm, which resulted in a maximum output current of 3.6 kiloamps. We also made sure that the turn-on time for the MOSFETs did not coincide with the activation or deactivation of the rest of the circuit. And then, so we found that the MOSFET board becomes fully conductive after the pulse from the gate driver reaches its maximum point, which is after about 41 milliseconds. And then the MOSFET board becomes fully conductive after 51 milliseconds. So it's about a 100 millisecond delay, which is good because we had a expected result of 100 microseconds, which is good because we had an expected result of a millisecond. And now I will pass it over to Juan.
All right. Hi, everybody. My name is Juan Rosas, and I want to conclude our presentation by saying that we have made a capacitive tab welder to weld nickel strips to lithium-ion batteries. The welder started to weld nickel strips at a voltage of around 12 volts and a pulse time of 20 milliseconds. And with our upper limits of 17 volts and 25 milliseconds, the user can perform more permanent welds, as well as use extra energy for other purposes. Our initial simulations of the discharge were confirmed through testing, and we were able to verify that the theoretical values we were close to the real world. While the predicted circuit resistance changed throughout the development, we were able to circumvent this issue by adjusting voltages and pulse times to achieve our desired results. These are our references, and we'll now show you the demo.
It's recording.
All right, this is our tab welder. The only thing we need to change currently is the connections, and we're waiting on the new PCBs to come in, and we should be done. But over here you can see us getting ready to weld. Let me turn it on. Right now we have it set at 14 volts for a 20 millisecond pulse, and we're gonna weld onto an 18650 battery. Ready, Juan?
Do it.
All right. All right. I did it. So now Juan's gonna. There's the battery. Wow, so strong.
Very strong.